Hello, hello. Welcome to the Chapter 14 video. Let me preface this video by saying this is not going to be super formal. I'm going to treat this as sort of a live stream video, and if something doesn't go exactly right in the moment, we are just going to roll with it. Really, what I wanted to do was give a high-level overview of some of the content in this chapter. This is really a big chapter with a lot of advanced concepts. And again, I just want to show the key components, architecture, and how the pieces all fit together to hopefully help you as you work through this chapter. So kind of what I would recommend is finishing out this video to get that high-level overview of what's going on, to read the chapter to understand the components and the concept. And then later on in the chapter, there's a link to a pretty heavy-duty tutorial called Secure Cloud Data Science that I put together, and that really goes step by step in how to deploy a well-thought-out machine learning application in a broader cloud environment on Amazon Web Services, better known as AWS. So I think that's really going to be where you get in the nuts and bolts of how to deploy an application on AWS, but there certainly is a lot of content in Chapter 14 as well. One point that I want to make is that you can apply these concepts overnight, but you can't necessarily learn everything holistically overnight. It takes time to really understand all of these components and how they stack together and how they connect. And it really there's just no substitute for taking the time to learn it. So really the goal, again, is to show you what to learn and give you examples for the components that you'll need when you're ready to learn. So what I thought I would start by doing is kind of going over a very simple sample application, and I have that up here, and it's also on GitHub. I will show you the link to that as well. But this is kind of a fake machine learning application. It functions like a real application, but it's scaled back in certain degrees, and it won't have all of the cool bells and whistles that our actual churn model application has. So again, what I want to do, and this video will probably take a little bit of time, frankly, because I want to go through several components here. But again, what I wanted to do was just walk through some of the main components of an application and what we're doing, just to kind of make sure you get some of the overarching architectural and infrastructure ideas on this. So to host and serve a machine learning application, you can use a web service called Flask. This is a very bare bones web server framework provided by Python. It's low level, but it gives us a high level of customization. So to initialize the Flask application, I simply need to call line 8 here. It's very simple to do that. And I have a couple of endpoints here, so it's kind of weird not to have a home route, so I just make that what's called a health check. I also have a specific health check endpoint. This is something that's actually used on AWS to help monitor if our container is actually up and available. And then we have the predict points. So this is where somebody could do a post request to actually get a prediction. So we load in our model, we take in the JSON request, we convert that JSON request to a data frame, and then we actually make the prediction and then return the prediction. This is a very scaled down use case here, but this could mimic something that you would want to do actually in a production setting. I do just load the model every time the predict endpoint is hit. In the applied data science repo, we actually have an initialize application function that will only load this once the application boots, and that's actually what we want to do. But again, for simplicity, I've kind of scaled this down a little bit. This is a fake model that is just in the modeling directory, but this mimics a scikit-learn model, basically. So this is something that you can use out of the box, and you don't have to worry about pulling down data and training a model. You can just go to model.py and see that this is just a class that has a predict proba method on it. It takes a data frame, but it actually doesn't use that data frame at all. It just will return a static prediction of 90% for the positive class. So again, we don't really care about the model so much. We just want something that functions like an actual scikit-learn model or an XGBoost model, or you have the framework. So that's the Flask application. And again, in the predict endpoint, that's where you're going to put the code to actually run your model and return the prediction. So that's the most important file here. We also have a helpers file, so we saw some functions called in app.py. That's where we house these. Again, we would probably want to do a helpers directory actually in production, but this is, once again, a scaled down application. Another important file is our Docker file. If you want more information on Docker, you can go to chapter 4. There's a pretty good, well, I hope good tutorial there, but more or less what we're doing is we're creating this environment where we can run our application. It has everything that we need. So it'll have, based on this base image, Python 3.7, it will have a Linux operating system, a Python interpreter, Python 3.7. It will have all of the packages that we need defined in requirements.txt. And then what will happen is it's going to boot up our server, and that will allow us to actually hit an endpoint, namely either home, health, or predict. And this leads me to run.sh. So it's somewhat common convention to have your command be a shell script, and this allows you to potentially run multiple commands if you need them, but really what we do is just run a single web server here. So we have our shebang here at the top, and we're using the Unicorn web server. So Flask does come with a web server that we'll actually show in just a minute, but it's not a production web server. You'll actually see that listed whenever we run it. It's not what we want to use in production. We want to use Unicorn, which is an actual production grade web server. So we have a couple of command line arguments we're passing in here, assert and a key. So this is public-private key. This actually allows us to have end-to-end encryption with our application. We'll kind of go over that architecture here a little bit later, but these are just self-signed certificates generated with OpenSSL, and how to do that is listed in the Secure Cloud Data Science tutorial. But basically, this allows us to have HTTPS even at the lowest level of our application by using these self-signed certificates. And then we bind to port 8000. Basically, this is just saying that we're going to run on whatever host or DNS is available to us at that time. And then we're saying that my application is just app here, basically. So run.sh is another important file. The Docker ignore, this is the same as the git ignore. We've talked about git ignore in the past, and I think I've mentioned Docker ignore previously as well. But basically, if we build a Docker image locally, we don't want to include any of these files as well. When we actually build Docker images going forward in production, those are going to be keyed off of our commits to a main branch in code commit. So the git ignore will prevent these files from being in our Git repository, but if we're doing something locally to potentially like seed a container registry, this is kind of nice to have. What else is in here that is good to talk about? So a lot of these YAML files are specific to our code commit pipeline, so our CI/CD pipeline. So that's not a term that we've talked about too much yet, but CI/CD is continuous integration, continuous delivery. And so that means that every time we push to our main branch in a Git repo, in my case, it's an AWS code commit repo, that's going to kick off a build. So that's going to build a new Docker image for us and automatically release that into staging and have a manual approval step and then release that into production. So we have to have some of these infrastructure scripts actually within our repo for that code pipeline, which is the AWS name for it, to work. So one of them is appspec.yaml. We just have to fill in a few things here for this to work. I'm going to come back to build spec because that's potentially the most important one here. There's a lot of things that we can do with that. We have to have an image definitions JSON file as well, and then a task def.json. And I've kind of called out where you need to insert specific references to your own assets in here. Build spec. This is a really important one, and this is actually where a lot of the magic happens. And again, we'll kind of go over some of this a little bit more later, but this is going to be kind of really where a lot of the magic happens. Again, pardon me, I'm going to take a quick drink of water. Again, I said we're just going to roll with things here. This isn't going to be super formal. So basically, this spins up in an Ubuntu instance is what I actually configured for. It could just be a Linux instance, or I think you could even do Windows if you wanted to. But basically, this is going to spin up a little compute power, and basically, this is just a shell script. This is just going to run a series of commands for us. So this spins up Docker. This installs our requirements and then runs our tests. So this has the benefit of if we have a failing test, our build is going to be killed, and that will prevent us from pushing bad code into production. So this is really important, and having a built-out test suite is vital if you're doing CI/CD. In my case, I only have one test. Again, this is kind of a toy demo example, but in reality, you would really want to build out this test file. We then log into ECR. This is our container registry. So we've talked previously about Docker images in chapter 4 of the book. And so you can actually host your image on a remote server. If you're wanting to do something in production that can't reach your local machine, so you've got to have that on a remote server. So we can use Elastic Container Registry in AWS for that. So we log in there. We're actually going to pull up our commit hash so that we can tag each Docker image with the commit hash to version things over time. We'll build our Docker image, we'll tag our Docker image, and then we'll upload it to ECR here. So basically, whenever we push to our main branch of our Git repository, that will kick off a webhook that will then run this script, and that will update our Docker image. And that's how we're actually able to release production changes. Is everything in production runs off a Docker image. This updates the Docker image, and then we have a deployment process that runs that actually picks up this new Docker image. So really, that's kind of the key repo files that we'll go over at this time. We have some infrastructure as code in here as well that we'll go over later. So let's kind of talk about what this actually looks like. We've talked about Docker a little bit here, but I'm going to bring up my terminal and run Docker images. And I have a few images in here. This one is example web app. So I'm going to copy that to my clipboard. I'm actually going to bring up a new terminal here. And we're going to do Docker run, and we have to bind the ports. I'm actually going to reference this on the website, secureclouddatascience.com, because I sometimes forget how to bind these ports. And then we want to remove the container whenever it stops running, and then we call this example web app. So this is the Docker image that we have locally. So we're actually going to run this and use this locally. So this boots our server. And again, all this is doing is it's running run.sh, which is just spinning up a web server for us. So we can see that this is booted, and we can see also that we're using HTTPS, which is kind of nice. So I'll just copy this guy real quick. We'll go to Chrome. This is running on localhost, which is 127.0.0.1, and we're on port 8000. So we can see that, yes, our app is healthy. And then we can also use Postman to run a prediction against our predict endpoint. Based on how the application is written, it doesn't matter what we post there. This could be anything. This is part of a payload from the churn model application, but as you saw in the code, we basically just ignore the data that's passed in and just return a static value. So if we hit this, we'll see that, oh yeah, there's an issue with Postman using HTTPS. I forgot about that. So we'll actually run this from curl on our command line. So I might have had the wrong port too. That might have been part of the issue. And then we need to do HTTPS. So yeah, now that works. So few hoops to jump through, but we can see that we can actually hit this web server that is running locally in our Docker image, Docker container, which is run off of our Docker image. So I'm going to clear that guy. We don't need Postman. And I'm going to Control C on that. That actually is not killing the web server. That happens sometimes. So I'm going to terminate that. I still have a terminal session that's up and running. If I issue a Docker PS, it will show me that this container is still running. I need to grab the ID and issue Docker stop. And any day now, this should stop that container. And it stopped, and if we reissue Docker PS, we'll see that the container is gone. This is because if you recall, when we actually issued our Docker run command, we passed in the --rm. So that tells Docker to remove the container whenever it is done running. So after we stopped it, it just removed itself. To kind of make this idea a little bit more concrete, we're going to go back and actually run Docker run again. But we're going to do something a little bit different. So we're going to issue Docker run. We want something called an interactive terminal. Actually, we're going to do rm first, interactive terminal second, and then we're going to do our entry point of bin bash. So that will actually take us into the container itself, and it's actually not going to boot up our web server. And then I believe it's called example web app. Unable to find. Oh, I think I have to pass in entry point as a flag. Yeah, forgot to do that. So this actually has taken us directly into the container right now. So this will kind of make the idea concrete that literally when we're defining a Docker image to spin up a Docker container, this is just coming up with an isolated compute environment for us. That is all that it's doing. So if I issue an ls, we can see that we have all of our files in here. We have our Docker file, we have our app.py, we can print that, and we can see that, yep, this is just the code that we came up with. If I do a pip show joblib, which is a library that's in our requirements.txt, we can see that's installed. So again, all we've done is just come up with this mini little compute environment that has everything we need for our application. I'll exit out of that and clear the screen. And that really is everything when it comes to Docker. So really the idea of our application is that we want to take this local Docker image and just be able to run this on AWS so more people can actually interact with it. I'm briefly going to show the web server that Flask comes with. If you need to test your application, outside of Docker, which is actually really useful to do if you're just kind of prototyping and toying around with things. This is a useful little just test web server. So we just have to add this boilerplate here. We can see that there is a warning. This is a development server. Do not use it in production. And if we go to localhost, by default, Flask runs on port 5000. In Docker, I specified port 8000. We can see that we are actually taken into the application. And this time, if I were to use postman, this should work for us. And it does. So one of the reasons that we run on port 8000 is because that is a port that allows us to run as a non-root user. Ports 443, which is for HTTPS Classic, and port 80, which is kind of your classic port for HTTP, require you to run as a root user. And for security purposes, we want to run our web server as a non-root user. And you can kind of follow these commands here and see that's basically what we're doing. We're coming up with an app user that only has access to the code in our folder, basically, more or less. There's a little bit more that's going on than that, but this is a security protocol. So if our container were to get hijacked, the hijacker would have access to a container that is running using a less powerful user. So that's a security protocol, and one of the reasons we run on port 8000 as opposed to like 443 or 80 or something along those lines. All right, time for another quick drink for me. This popped up a second ago, but let's kind of talk about what the architecture of our AWS application looks like. So this is really simple. There are more moving parts to this, but at a high level, these are the main components that we have. So again, what we want to do is we want to have multiple Docker containers running, just like we did locally, but we want to put them on AWS. And we want to have multiple copies in case we're getting a lot of traffic. We want to be able to load balance this. So our actual applications are sitting here. They sit behind a load balancer, which will divvy out traffic to each of these different instances. And then on top of that, we have Amazon Route 53, which provides DNS. So your application load balancer will have this big, long DNS name, but we ideally want to have a cleaner DNS. So for example, I've deployed two applications. They're the same, but it's just staging and prod versions of it, which is best practice. And we can see that we are hitting stage example at .allstardatascience.com. So this is a lot more friendly DNS. Back to our diagram. So actually throughout this, there's a bunch of security layers. So we have something called the security group, which only allows certain IP addresses or certain resources to access this. So for example, for our application load balancer, in my specific use case, I am only allowing my IP address to hit this application load balancer. And whenever I hit, for example, prod example app.allstardatascience.com, this just forwards traffic to the ALB. It'll forward the IP address and it'll get blocked. There's also something called a web application firewall here. So we actually have kind of two layers of security here. We have a WAF and then a security group. And then there's also a security group that protects these containers here. And actually the way the security group is set up, it's so that only the application load balancer can get to these. Only this specific resource here. So I cannot, using my IP address, go and hit these containers. And another security protocol is I actually have these running in private subnets. These do not have a public IP address. So it's kind of a double layer of security here. And this communication here is only happening on AWS's internal network, which is pretty nice. And again, on this level, based on this call here, cert file and key file and kind of passing in that public-private key. Again, I don't mind exposing these because they're just self-signed certificates. And when those are getting used, those are actually just getting used over AWS's private internal network. But if there were a internal bad actor, this would make sure that this traffic is also encrypted here. So we have an SSL certificate that protects here. We have these self-signed certificates that protect here. So we are actually enforcing end-to-end encryption here, which is kind of nice. All right, so how do we actually create these resources within AWS? We have talked about Pulumi a few times throughout this book, and that's what we actually use to create these ECS applications. So this is a big, long script, again, that just creates this whole guy right here, basically. And this will be posted in the repository. There's a doc string here that explains all of the parameters. And again, there are a lot of components to this. So why do we create a Firehose role? Firehose is for Kinesis. Basically, this is how we log using our web application firewall. So we have to create permissions for that. And there's a lot of boilerplate code that's involved in that. This is where we create the stream, again, that's needed for actually logging when we're using our web application firewall. Here's where we actually create that web application firewall. We create a role for our ECS instance. This just basically allows these containers to act as tasks. More or less, it's a little bit more complicated than that. If we need to attach specific policies, we can do that. So we may have a need in one of these containers to reach out to a, for example, S3 bucket. We can have an execution role that has permissions to very specific AWS resources, and we can define those here, basically. So what exactly might that look like? I'm going to go to IAM. Go to, reloaded on me. So we're going to go to policies. Yeah, these are all, I want to see if there's an S3 one, for example. Yep, so this is a policy. It's just JSON, basically, that allows any user with this policy to only have access to this specific S3 bucket, which has since been deleted. So you don't try to go here, that S3 bucket is gone. So what we can do is we can write those specific policies and attach them to the users that are actually running these containers here, and that will give us increased security. Again, we've already talked about how secure these containers actually are, but we always want to be enforcing best practices in case we accidentally misconfigure something. We always want to have those buffers of security. So we can do that here. We create something called an ECS cluster, which is just like a big container. I'll show that in just a minute. This is where we create our security group for our application load balancer. We talked about that. This is where we create our security group for our ECS instances. Whenever I say ECS, I just mean containers. So ALB, application load balancer here, ECS containers here. This is where we actually create the load balancer. We also create something called a target group. Basically, this allows the containers and the load balancer to communicate. So the containers can say, hey, I'm healthy, or hey, I'm not healthy. So this is kind of enables the communication between, again, load balancer and container to identify what's healthy, what's not healthy. We have some listeners for our load balancer, so we want to listen on different ports. This is where we actually kick in our web application firewall Route 53 record. This is where we create our domain name that will actually map to our load balancer. So that's what happens here. Request to Route 53 gets forwarded to load balancer. Again, there's a lot of things here. Log group, we enable logging here. And then task definition. So whenever we're running something on ECS, I've used the term container before, which is accurate, but these are also referred to as tasks. So we want to come up with a definition for what these tasks look like. And we can see that we need to specify what's the Docker image that we want here, what's the port. I pass in some environment variables here as well. And then a service is another type of container to basically house multiple tasks. Again, there's a lot that goes into here. There's a lot of components, a lot of things that are stacked together. I don't expect you to understand all of these off the bat, but these are all of the things that come together to make up a full throttle application that's secure, I hope secure, end to end at the very least. I will note, and I have called this out in Secure Cloud Data Science, the Web Application Firewall, or WAF, resources with Pulumi I found to be a little bit finicky. So a lot of times they'll fail initially, but if I rerun them, and you can just run just Pulumi up is how you deploy your infrastructure as code. Sometimes I have to run that a couple of times to actually get those to create. It could be something that I have wrong in these scripts, but I've just found them to be really finicky. And sometimes they actually will create, but they will be empty or won't have something that I specified. But the good thing is that I've actually created everything, so I can kind of just manually do a little bit of linking if needed. So just wanted to call out that these can be a little bit finicky. And if you have issues with this script failing, you may just have to kind of like repeatedly run it until it all goes through, and then check things with the Web Application Firewall to see if you need to manually connect anything at the end. But everything else in here does work like a charm from my experience. So let's take a look at what this actually looks like in AWS. So let's go to EC2. And we can go to load balancers. And we can see that I actually have two load balancers, one for my prod application, one for my staging application. So this is what, again, divvies out traffic to the underlying tasks or containers. Whenever we specify our subnets for these, they need to be public subnets. I kind of talked about public-private subnets a little bit earlier, where we ideally want these to be in private subnets, so they have no public IP address, but we need to make sure that the subnets that we specify for our ALB are public subnets, given the infrastructure that I've built out in that infrastructure as code script. So these sit here. We can also look at our target groups. Should have two of these as well. So we can see that we have some health checks set up, and this is what communicates, hey, is the underlying container actually healthy? Is it actually working here? There's some monitoring here as well. So it'll kind of talk about healthy host, target response times. We just have one healthy host. We only have one host that we care about right now. So this all looks pretty good to me. And if we go to the details, we can see that underlying we have one healthy container, and that's all we want. We could easily spin up multiple tasks or containers. Again, I'm kind of using those terms interchangeably, but we can see that it's healthy, which is what we want. Let's now actually go to ECS. So at the highest possible level, we have our cluster. This doesn't really do a whole lot. Again, it's just like the biggest possible container. And both of these are basically identical. One's just running a stage application, one's running a prod application. Those are identical. But again, on a staging environment, we can kind of play around and make sure that everything works. But we only want to push things to production that we're absolutely sure about. So we have our cluster. Underneath our cluster is our service, and our service can hold multiple tasks. In this case, we only have one task, and we can see it here. And it is running, and if we go to this task, we can see that It does not have a public IP address, which is exactly what we want. And again, in this instance, only our load balancer can talk to this task. And then we also have Route 53. I'm not going to go there, but that's just pretty simple DNS offerings. Go back to the home screen here, and let's go back to PyCharm. That's not the repo that I want. This is the repo that I want. One other quick note is you can see that I have two folders, one for staging and prod. Again, these are basically the same things. I just basically am calling things slightly differently, and depending on our environment, we may have slightly different underlying infrastructure choices that we make for staging and prod, such as what databases we allow staging resources to have access to. All right, so we previously talked about CI/CD, or continuous integration, continuous delivery. So again, to repeat myself, the idea is that once we push code to our main branch, we want that to kick off a build. We want it to test our code, and we want it to release it to staging. And in my case, I have a manual approval step, and then if I approve it, go on to prod. So this creates that pipeline. We can see that we have to create, again, some roles here, making sure that we're giving the actual resources that are running these scripts and running these deployments the ability to access the resources that they need to access. So we're just setting up permissions there. Code build. So we talked about our build spec file. Code build just runs this. That's all that it does. It runs this. So this step, well, actually, we're just defining the project here. We'll define the step later. But this just defines the code build project that, again, all that's going to do is run build spec.yaml to update our Docker image. And as we talked about, we can see that we're just spinning up, like, in this case, a Linux container. It's actually, I think the underlying operating system is like an Ubuntu flavor of it. We need to make sure that we run in privilege mode because we are running Docker. So we configure all of that there. I also run this in a private subnet. One of the benefits of a private subnet is that it can sit behind something called a NAT gateway and be attached to an elastic IP address. The thing about an elastic IP address is that it will always be the same. In a subnet, you could get a range of IP addresses, but if you attach it to an elastic IP, you'll get the same IP address every time. And we've talked about having a private Python package a lot in this course. So by running this in a private subnet, I can whitelist that single IP address in whatever we're using to deploy that package, whether it's S3 or an ECS instance. I can list that IP address and make sure that our code build project can install it. And here's where we actually define the pipeline, so we can see the stages. And this will make a lot more sense, I think, once we actually show it in AWS. So we have a source stage. So this is just code commit. So whenever we push to our main branch, we will kick off a build. So that grabs the actual code. We run our code build project here. Again, just running build spec.yaml. We deploy to stage. We have a manual approval, and then we deploy to prod, and then we just kind of finish up with some permissions here as well. So again, to run this, we would just have to cd into this directory, run pulumi up, and that should deploy everything for us. And again, this has a large number of arguments to it, but you can see that we have a doc string here that should explain everything, or hopefully should explain most everything. All right, let's take a look at what this bad boy looks like actually in AWS. So we'll go to code pipeline. So again, we have our source step. This will peg to a commit. So if I click this guy, that will show the commit that actually kicked off that build. We go to our build step. I said step really weird there. Step, I should say. This video has been going on for a long time, so please forgive me. Again, like I said, we're just going to roll with the punches. If things don't go exactly right, we're just going to roll with it. So we build our Docker image there. We deploy to staging, and here I have my manual approval step, and if I approve that, that goes on to prod. So we can see that this ran successfully, and this is how we want to release code into production. We want to push to Git. We want to grab our code automatically. We want to test and build that code. We want to deploy it to staging so we can verify it. And if we're really good, we can remove the manual approval stuff. If we have a really tight and thorough test suite, we can remove the manual approval and just go to prod. That's ideally where we want to go, but sometimes having this little buffer here is pretty nice. So this is exactly what we want to do to release code into production. So that's, again, really the architecture of all of this. So there's a lot of components that go into it. This will be, it's not the repo that I want this repo. So all of this is on GitHub. So if I go to GitHub real quick, go to my repositories, click on this guy, we can see that everything is here. Everything is here, so you can review this on my GitHub. It's just example web app. And again, the idea is that this is something that you can just pull down and apply. You don't have to worry about pulling down data and training a full model. The model.pickle here, produced by model.py, it works, like a model that would be in scikit-learn, basically. It doesn't work exactly like it because it only returns like a single component of the array. It's not a multi-dimensional array, but it's good enough for what we're trying to do here. All right, so really the last thing that I wanted to do, now that I've talked about these kind of simple use cases to a degree, I wanted to dive into the Flask app that's actually in applied data science. And before I do that, again, apologies, I'm going to take another drink, but you can kind of soak in while I'm doing this initialize app function. All right, so in the last video, we actually saw in our predict endpoint that we loaded our model each time. We don't really want to do that. And so we can run this initialize app every time that our server boots to do kind of some of these setup things. So I'm just going to kind of run through this line by line. So this is how we actually initialize the Flask application. That's the object that we return. We set up something called Sentry. So this will alert us to errors. So anytime we get an error in our Python code, this will report it to Sentry, and we can set that up to email. So it's very simple to set up, very effective. We've talked about configurations, or we've at least mentioned them a little bit, and that's definitely discussed more in chapter 14. Your application is actually a combination of code and configuration. So a configuration may be that if a predicted probability is above a certain threshold, we're going to give it some type of an automatic classification. So we actually read in our configuration from a MySQL table. Later on, we talk about the idea of infrastructure as code. Configuration as code. We've already talked about infrastructure as code. We talk about configuration as code, where we treat our configuration as what's called a first-class citizen. We can version and track our configuration changes over time. We can deploy them independently. We don't have to deploy our application to deploy a config change. We want those to be independent, and we also want those to be able to be tested independently. So if we had a config file, just a flat file in here, we wouldn't be able to do that very well because we would have to deploy our application to deploy a config change, and we don't want to do that. It also may be difficult to kind of separate out some of the testing as well. So basically, we have our application living in a MySQL database, and so we can just read in that configuration and apply it. We also may make configuration changes after our application is booted. And so we actually run something called a background scheduler to check for configuration changes. In this case, every 3,600 seconds, we could probably lengthen that out a little bit, but this is necessary because, again, we may not want to keep these original config values. We want to change them. We need to check for these changes. And how do you communicate with an API? Well, you communicate with an API via GET and POST requests, and that's why we have this function hit config refresh endpoint, and this will actually refresh our application configuration. So really, for configuration as code, this is just a logical application for how to do this, and this was really inspired by Google's SRE, Site Reliability Engineering Handbook, where they talk about configuration management, and they kind of talk about having user interfaces for configuration management. So a lot of what I've done was really inspired by that. And then here we actually load in the model. So we declare it as a global variable so that it will be available outside of this function. And we load in our model here. So upon our application booting, we're only going to load our model once because we don't need to have all of that I/O on any given request. So that's where we run the application. We initialize our application. Talisman is a library that provides some basic security for Flask applications. You can kind of read about it on your own. One thing that it does that's really nice is that it automatically reroutes HTTP requests to HTTPS requests. I need to actually remove this guy here. I'll have to remember to push that. That was clearly a typo. I removed that functionality. We have a secret. This is just for cookies. There's something called the Flask monitoring dashboard, so we actually initialize that here, and we can go to that endpoint to kind of talk about that. If you want more details, just search Flask monitoring dashboard. And then Swagger is a way that you can actually look at API documents. So this will automatically generate API documents from our docs strings, which is kind of nice. And then I think the endpoint is like API docs or something along those lines that's talked about later. I think that's actually talked about maybe in chapter 16. But we can actually automatically generate documentation from our doc screen. So that's what we're doing here. So we're just kind of doing some basic setup here, and these are only run when our application actually boots up on ECS. Here I assign a unique identifier to each request. We have our home route, which again, it's just weird not to have a home route, so I just use this as a backup health check. We have the health check endpoint. We've kind of talked about those in the past. I'm going to skip over a few of these other functions that are in here because they're kind of for later sections on, and they're not necessarily as important. So we've built a little user interface into this in addition to like a predict endpoint that can communicate over REST. So we have a login, a logout. Model interface is where we can actually go to a user interface and kind of interact with the model a little bit. This is just kind of plain old HTML, nothing special about it, but we do have a mechanism here to check if we're logged in or not, and if we're not logged in, that's going to redirect us to our login. Config refresh, we talked about that already. Again, configuration as code is something that's really important, and to implement configuration as code, we need to be able to update configuration without redeploying our application. A logical choice for those configuration values is in a database table that we can read from. And again, how do you communicate with a REST API? It's through GET or POST requests. So anytime this configuration is hit, we're going to retrieve our application configuration and just apply that here. Again, this is just a really logical application of this. And again, the Google SRE handbook was really useful for this. And then we have our predict endpoint. So we can see that this is a bit more involved than what we had in kind of our toy example. We're receiving our JSON. We're actually reading from another table as well. We're looking up a client's LTV, and this is a function that's cache. So we have a TTL cache on this that's time to live cache, or time to live cache is probably the better pronunciation for this. And we have this valid for a day. So we'll run this once and then keep it in memory for basically a full day. And the idea is that these values probably aren't changing that quickly. So, if we read it once, we can have it stay valid for a long period of time. We kind of saw some code earlier on converting JSON data to a data frame, making a prediction. Here's where we actually use the config. So again, you can see that this is important. And this is something, again, that we may want to toggle without redeploying our application. So proba cutoff, if it's above whatever value we have in our config, we'll flag it as high risk, else it's low risk. The 0.75 is a backup. So this is actually a dictionary. And so it has this .get method. And so if we didn't define proba cutoff in our config, it would fall back to 0.75, which is a good way to write defensive code. We're just kind of logging some things here to our input and output dictionaries. We print our response, and then we return our response. And as you can see, we kind of wrap this in a try except as well. So if we error out here, we'll print our exception that will log it to Sentry so we can see it actually in our AWS logs by printing this here. We will log that to Sentry, so we should get an email, and then we'll just return this kind of stock prediction. In this case, what you return here is just going to be contingent on your situation, but in this case, I just kind of said, all right, we're just going to return this simple JSON. And then finally, so we have a try except finally, if we're not in our local environment. So if you recall in our infrastructure as code scripts, I briefly mentioned this, that I set some environment variable. So if we're in staging, we'll set an environment variable called stage. If we're in production, we'll set an environment variable called prod. And so this will help us know like what environment we're in. So if we're not local, because we don't really want to log if we're just toying around with things locally, what we'll do is we'll basically just log our payloads to S3 and MySQL. In this specific case, we don't care that much about response time. So if we have to wait a few more seconds, not a big deal. If we were running a Kubernetes app, we could offload these onto a Redis task queue, and I actually discussed that and kind of show that later on in the chapter. But basically, we always want to log what's coming into our API and what we're returning. And the idea is that this is set up in such a way where even if there's an error here, we're still going to log what we got, and then if we had anything in our output payload dictionary, we'll log that as well. So this is kind of set up in a pretty defensive way. And I need to delete that import statement as well. I was kind of playing around with some things in Redis and forgot to delete a few things. So again, we're in our application, we're just using Flask to serve our model. We can write straight up Python code for this. We're using infrastructure as code, which is the best practice. We're using configuration as code, which is best practice. If you just Google search something like infrastructure as code or something like configuration as code, you're going to find a lot of resources that's going to talk about a lot of the things that I've talked about. So I got a lot of inspiration from Google and Google itself, and then also by Google searching too, but you can also see the citations that I put in this section as well. One thing that did occur to me, I didn't actually test out the applications that we deployed on ECS. So I'll just kind of copy and paste these so we can see that our stage app, if I hit like our just home route, app is healthy, we're good, copy this, hit that, we can see that app is healthy. So both stage and prod applications are running, and we can see that we have this nice little DNS. So, that's running down to our load balancer, running down to our task, and then running back up the line. And again, we can kind of hit these with curl as well. So if it doesn't matter which one of these we hit. Using HTTPS, we can do our predict endpoint, and yes, we get our static response. So this works, it's going over HTTPS, we have our SSL certificate as well, so it's really nice that we can kind of set this up to be hit that way. All right, I think that just about does it. This was a really meaty and long video, but I wanted to show the scope of what was going on. Again, just walking through a really simple example that does mimic a production model, looking at all of the components, the infrastructure as code, the configuration as code, CI/CD. This covered a lot of ground in a short period of time. I can tell that this video has been going on a long time. I'm starting to lose my mind and also lose my voice as well. So I'll wrap it up here shortly. But you can apply this stuff overnight, but you can't necessarily learn it overnight. This is a really difficult and involved chapter that goes really kind of in the weeds on a lot of different things. But I wanted to introduce you to a lot of concepts and give you resources for when you're ready for them. So actually what I would recommend is that if you want to build this type of application, like spin up some things on ECS on yourself, for yourself, and then add on a load balancer, then add on DNS. Kind of do it piecemeal, set it up yourself, and then once you understand everything and how it all goes together, then you can start using the infrastructure as code scripts. But hopefully this will give you a flavor for all of the components, the architecture, the infrastructure, how they all fit together, the whole idea, why they're beneficial, and you can learn on your own and then kind of use these resources along the way. So I think that about does it. I appreciate you tuning in. This was a long one, so I hope you found it beneficial. Thanks, and I hope you enjoy chapter 14.